In this lecture, we're going to talk about measurement, things like scales and how we measure things. And in today's lecture, we're going to talk about measurement. And the driving article for this discussion is the Brain Injury Vision Symptom Survey, BIVS, that questionnaire. When we talk about measurement in today's context, we're mostly talking about questionnaires. And this is a study validating a brain injury questionnaire. It's self-administered, and it looks at trying to detect people's symptoms that are brain injured and compares them, in this case, to controls, which were optometry students. So the first thing we talk about when we talk about measurement are data types. Now, you probably had this in previous statistical classes. They're nominal. Those are categories of items. They have no particular order. Things like colors, animals, days of the week. Well, days of the week kind of have an order, but not really. And then there are ordinal variables on a scale from 1 to 5, 1 to 7, 1 to 3. There's an order there, but it's not an interval. So the difference between 1 and 2 and 4 and 5 is not necessarily the same. But the order, 2 is greater than 1 and 5 is greater than 4, that is the case with ordinal data. Interval and ratio data are things like interval would be like temperature. In Fahrenheit and Celsius, there's no absolute zero. But the difference between 0 and 1 and 32 and 33 and 100 and 101 is pretty much the same. A ratio, if we were talking temperature, would go to the Kelvin scale or some scale, or say height. So if you're 6 feet tall, you're twice as tall as if you were 3 feet tall. So ratio are ratios with an absolute zero, and you can use certain types of data with ratios. We're going to also talk about latent variables a little bit. Latent variables are unobservable variables like fear, pain, things like that. And how do we can't really see them directly, but we develop scales and surveys to kind of get at where are we on a scale of, say, pain. So on a scale from 0 to 10, how much do you hurt? 5 is kind of in the middle, kind of an intense pain. 0 is no pain at all. And that can be treated, is usually treated, well, that is basically an ordinal scale. The difference between a 9 and a 10, most severe pain, is not necessarily the same as between 0, no pain at all, and 1, just a very little bit of pain. So we talk about Likert scales. Those are basically ordinal scales. And if we want to do statistics on Likert scales, we have to do statistics on ordinal. And there's somewhat of a debate about that, and we'll get into this a little bit later. But Likert scales, there are a lot of people who say you cannot take the mean and standard deviation of Likert scales because ordinal data, because those unequal intervals, you're not able to do that. And so you shouldn't take the mean. So people talk about medians, percentiles for different things. Rush analysis is a relatively newer method. I mean, it's not really new, but it's been around for a while. But people in optometry haven't used it until more recently. In Rush analysis, you can take a Likert scale that's an ordinal scale, and you basically say, well, how many people said, pain was 1, or how many people said pain was 2? And you look at kind of you use the frequency of responses rather than the numbers on a scale to determine how much something is. So, for example, if 100 people said they didn't have any pain, 5 people said they had a fair amount of pain, then, or 4, you get this scaling, and you can actually, through some statistical manipulation, convert these numerical scales of 1 to 10 to ratios and logits, and we'll talk about that a little bit more in today's talk. Well, there are many uses of scales. We're all familiar with the eye chart. If the big E, you can see that, you're in good shape. If you get down to 20/20, you're in better shape. You're considered normal. A normal vision person can see a letter at 20 feet and an arc of 1 degree. Letter height at an arc of 1 degree at 20 feet. They have 20/20 vision. Attitudes. Are your patients satisfied with your service? That's kind of a scale. Competency. Life tasks as a function of visual competency is a competency. Can you walk? Can you drive? Can you read? These are different functional competencies that are used. Symptoms. What about dry eye? Do you have dry eye? How bad is your dry eye? And the BIV scale, is symptoms from traumatic injury. How severe are your symptoms? Those are scales, and the more severe, of course, at some point, if your dry eye is bad enough, you'll get prescribed medication for your dry eye, or start worrying about it. If it's just a little bit dry, maybe not. So you want your scale to be relatively consistent in finding people who have symptoms, and the various degrees determine how much you have to pay attention to helping them. So basically, the purposes of a scale is to locate a person's point along an underlying unobservable dimension. That's the latent variable. And generally speaking, you can have many latent variables. For example, we've at the Vision Performance Institute, we developed a scale of symptoms, and you had internal symptoms. That's kind of, if you think about it, inside your eye, pain inside your eye, ache, maybe headache, versus external symptoms. And those are symptoms outside, like itch or a pain outside on the outer portion of the eye, and dry eye, that sort of thing. Those are two unobservable dimensions: internal symptoms, external symptoms. And you can have either no internal symptoms or a lot of strong internal symptoms, and those differ from no external symptoms or a lot. And they're kind of, sometimes they're correlated a little bit, but they don't, they're still considered separate latent variables. And you take out or you ask various questions to try and find the position on that scale. In this little example, we have two people. One person is located kind of on the happy end of the scale. They don't have very many symptoms. And another person has a lot of symptoms, or strong for each question, and they're unhappy in terms of the amount of symptoms they have. So their scale point on this underlying dimension that you can't see is truly here or there. And we're going to talk about that a little bit. So one of the ways you do that is with a Likert scale. It's introduced in the 1930s in conjunction with a massive national attitude survey. I encourage you to look that up. It's a pretty interesting survey. Questions have a response scale that is ordinal. Strongly agree to strongly disagree. There's an order like that. Never or always, that's another dimension along there. We go scale 1 to 5, 1 to 7. So there's a lot of people that say you can't take the mean of this because the intervals are not equally. Well, when is it okay to consider a Likert scale and to take the means of it? Well, first of all, the items have to describe the same underlying construct. The item responses have to cover most of the range of the construct. That's generally a good idea. And the items are linear related to an underlying normal distribution. Now, we kind of think of a normal distribution as a bell shape, but they can be lined up with an underlying cumulative normal. So, for example, if you think of symptoms and you're going to optometry students, well, most of them don't have any symptoms. Most optometry students, their eyes are fine, but there's a number where they're, after fine, they start accumulating symptoms a little bit. And so there's a little bit of a scale, but if you think about it, it's not the symmetrical thing where on a scale from 1 to 7, the most optometry students are not 4. They're mostly 1 or 0 if your scale goes from, say, 0 to 6. Instead, the scale is quite skewed, where most people are 0, a few more 1, a few more 2, a few less 3, a few less than that 4, and so forth. But if that matches the same percentages as a cumulative normal distribution, think of, for example, the right-hand side of a normal bell-shaped curve, then the numbers, in fact, the way Likert did it was he took z-scores, and if they followed the normal distribution, then the intervals were actually equal. So if you test a Likert scale and the intervals follow this normal distribution, then you can make a case that in terms of z-scores, the intervals are equal and you are allowed to take the means and standard deviations. So a Likert scale is not always, even though it's an ordinal scale, not always not a good statistical form. Sometimes it can be, but when you're reading a paper, you should be sure that the author has checked that. You don't see that very often. A lot of people just take the average and be done with it, but it's a good idea to make sure that the distribution is at least cumulatively normally distributed. And a lot of people think of that as a bell-shaped curve, but you can think of it as a skewed distribution. For example, the right-hand side of a bell-shaped curve, where most of the people are piled up at one end, and you can't see the good stuff. So you know that all the non-symptoms, how your eye feels good, are all piled up into a 0, where there could be, yeah, I'm good, I have no symptoms, or my eye feels kind of good, or really good, or super good. You don't see that part of it. It's all piled up into a single variable or a single character 0, and as no symptoms. No symptoms combine all the different levels of goodness, and the symptoms start out with respect to badness. But that's can be a cumulative. So you accumulate all the good stuff into one starting place, and then you look to see what the rest of the values are. The more questions you have, the better the mean is identified, the more accurate it is. Remember, the idea of this mean is to locate the point on the underlying scale where the person falls. Convergent insufficiency symptom scales and the brain injury symptom scales are examples of Likert type scales. The BIVS was divided into 8 underlying separate latent dimensions. The convergence insufficiency symptom scale is just one dimension, though I suspect it could probably be divided into several. Now we're going to talk about the BIVS, and the paper you reviewed looking at it and doing regular parametric statistics on the Likert scale from the point of view of taking the averages of the number, and it has multiple underlying latent variables. But it's also considered under a Roche analysis because those variables are not all that independent and separate. They're mostly that way. But you can also consider the BIVs as a single underlying scale, and you can get an answer from that. So you can do it either way in this case. Now let's take an example. Let's go back to our original thing where we had the little happy guy down here. This is a subject. And we had an unhappy guy who had a lot of symptoms. And then we asked them 3 questions. Now, the questions, each of the responses have a location on this underlying dimension. You can see that these particular ones aren't necessarily equally intervaled, but if they answered 1 and 2, they're kind of down at this end. The one rule that kind of applies is ordinal data is always 2 is greater than 1, 3 is greater than 2, 4 greater than 3, and 5 greater than 4 on this underlying scale. But you can see the little happy guy, his truth falls in between the 2 and the 3, and it's really closer to a 2. So the person would likely say for this first question, whatever it might be, he would give a response of 2 because that's the closest. The sad guy, he has a lot of symptoms, but this particular question doesn't go out the full extent of the scale. It's kind of up here at this end, and so the closest number to him is a 5. So we have a 2 and a 5 by these 2 different people. On the next question, the 1 is kind of far up the scale, and so the little happy guy says, well, my closest number is a 1, so he'd give a 1. And the 5, even though it's on the other side, it's closer than the 4, so he'd give a 5 to this answer. And this question, it's kind of separated in the middle, but it's closest to 2 over here and closest to 4 at the other end. And if you add up all those numbers, the 2, 1, that's 3, and 5, divided by 3, you get 1.67. That's the point on the scale. And this one over here, it's 5, and 5 is 10, and 4 is 14, divided by 3 is a 4.67. And that's what you would estimate the underlying point on this scale. And, of course, the scale ranges from 3, 1 plus 1 plus 1 is 3, to 15. 5 plus 5 plus 5 is 15. Well, and actually, if you take the average of the 3, it goes from 1 to 5. So this guy's out at 4.67. This guy's at 1.67. So that's the Likert scale. That's most articles that you will see will be measured that way. Optometry and vision science went through a period where everything was Roche analysis. They've kind of backed off from that a little bit, but I find that the Roche analysis is most appropriate when you're measuring competency and ability. I think Likert scales are most appropriate when you're looking at attitudes or feelings or symptoms. But because a symptom, for example, your eye could be dry but not achy or something. And the difference, or not dry, but it doesn't hurt on the outside so much. But this dry feeling is there. Inside you might have an ache. Somebody else might have a mild headache, or somebody else might have a mild headache but not the ache. There's not an order to them. They're just different ones, but they're kind of along. You kind of take the average to get the score. In a Roche score, you measure competency or ability, and there is a very distinct order. So, for example, if you can't see at all, you have the lowest visual competency. But if you can see well enough to walk, you're a little bit better. And if you can see to drive, you're even a little bit better. If you can read a newspaper, better still, and thread a needle, even more better. There is an order based on the competency, and the idea is that the scale seeks to find a single point along an unobservable dimension of finding this competency. An example of visual competency is the eye chart. Now, in the case of the eye chart, each letter is like a question. Can you see the big E? Yes. Can you see this big F and big P? Yes. Can you see the TOZ? Yes. Can you see the LPED? Sure. Can you see PECFD? Yes. Can you see EDF? Oops, I can't make out that one, but that looks like a maybe I don't know, a Z, a P, and you start screwing up here. Well, at the point you start screwing up, you can see everybody that's bigger than that, but you really have trouble seeing the items that are smaller. So there's kind of like a point along this competency scale. And when you're doing Rosh analysis, like the more people that can get a letter, the easier the letter is. And the fewer people that can get a letter, you rank each of these. And as the frequency goes down, the letter is harder. The scale is more difficult. The question is more difficult. And people miss it. And at some point, a person stops and they can see everything above and nothing below. And that's their level of competency. That's their point along the single dimension. It's very important when you're reading and reviewing an article that uses Rosh analysis, or when you're being critical of the article, you want to make sure that they are in fact measuring a single dimension. There's a lot of things, like for example, if you were doing the VPI's symptom scores and you were mixing together internal and external symptoms, well, then you wouldn't necessarily know where a point is on a single dimension because there are two, and to try and force that into one dimension could be problematic. Now, one advantage of the Rosh analysis is that you can locate both a subject and an item on the dimension. So if we look at our eye chart, the E is located on this dimension of visual competency. But a person is also located there. If they can only see the E and nothing below it, they're ranked up here. So in the Likert scale, you just get a mean of the person for the dimension. You don't get the individual question singled out so much. The data is not based on average score, but the proportion of people who are competent with the question. And the position is based on something called a logit, and that's the log of the probability of people that got the question right divided by 1 minus the probability that people got the question right. And the logit has a range from minus infinity to plus infinity with a mean of 0. The log is the natural log, and this procedure turns any question into interval data based on the proportion answering in a particular way. So Rosh analysis doesn't have to worry about making sure everything is cumulatively normal. It just works to give an interval point, and the point between questions isn't necessarily equal. You don't have to have that equal interval stuff. It gives you, based on the proportion, the frequency of people who answer a question, that gives you the interval data. So we have two different types of measurement scales, and they are appropriate in different situations. Likert scales are best for symptoms, feelings, attitudes. Rosh analysis is best for measuring levels of competency. Some people in the Rosh world try and put everybody in that same bucket. I think that's not necessarily appropriate. Feelings, people can have different feelings. And it's not just a dimensional thing. I mean, it is a dimensional thing to a certain extent, but you would just have too many dimensions if you tried to put everybody in every question in its own little bucket. But in both cases, when you're adding things up, the underlying unobservable scale is one dimension. So you're either talking about the internal symptom score, or you're talking about some competency in terms of visual ability. You want in a Likert scale, you want the responses for each question to cover the range of the underlying scale. And in the Roche analysis, each response represents a point along the scale. The response to each, in a Likert scale, the response to each question represents the person's location on the underlying scale. All questions measuring the same location on the scale. Many replications give an accurate representation of the location. In a Roche analysis, it's the point at which the person is likely to miss the question 50% of the time. And that's the person's point along the underlying scale. So they have a series of questions that are ordered in terms of competency, and the point where the person is equally likely to get that question right is the point at which the person lies on the scales. In the Roche analysis, items are ranked in order of difficulty. Then if a person gets a question correct, then all easier questions should be correct. If a question is missed, then all more difficult questions should be missed. The appropriate summary statistic for a Likert scale is the mean or median. A sum can also be used. Now, in the paper that I gave you to review, we did it two ways. We did both a Likert analysis, which using a factor analysis, we won't go into too much about what that is, other than it just suggests different latent variables. It yielded 8 separate dimensions, 8 separate scales, unidimensional scales. The peripheral vision, that's this one on the end, whereas these are the brain-injured patients, and these are the optometry students. I should say that the two TBI patients, when we submitted this paper, we just had TBI patients, and they said, well, you should look at the scale with an age-matched range. So the hashed mark, light-colored filled-in bars here, are TBI patients that match the age range of the optometry students. And so peripheral vision, questions related to that, for example, what looks straight ahead isn't always straight ahead. If a person said that was a frequent symptom, then that's the kind of information that was most discriminating between TBI patients and optometry students. Now, an interesting thing is these questions. So dry eye. Notice here are the TBI patients. And by the way, the scale over here is based on this. These are actually standard, they're Z-scores. And so this value right here is 9 standard deviations greater than these two. And we know from our effect size stuff, 9 standard deviations is pretty darn big. And here, the difference isn't quite as big, but notice there we have this line right here, our third-year optometry students with dry eye at about a 0.25 standard deviation above the mean. And these are TBI patients, about a half to 3/4 of standard deviation below the mean. So that's about almost a full standard deviation difference between third-year optometry students and TBI patients. And in this one, these are first year, and they're significantly different from each other. Now, this is kind of interesting because the first year students, Dr. Laukkanen distributed this questionnaire when they were coming in for their initial visit to, their first day, orientation. They were coming to orientation for school. these poor souls had to take this little test a week before they took their board exams, and they were studying like crazy, and their eyes were dry from all this open bookwork, looking at the computer monitors, staying up late at night, and their symptoms, they were symptomatic of dry eye, whereas the TBI patients were not symptomatic of dry eye. They also experienced some double vision, and that was not a particularly good symptom of TBI patients. So you can make, we developed a little worksheet. So we scored everybody taking a TBI or taking the BIVs, and you can see profiles of different patients based on where they are on these 8 different dimensions. Now this is the brain injury symptom survey with a Roche analysis. And basically you have this, the question here is, do the variables kind of go along if you're right on this line, you're good for a unidimension. If you're spread, if you deviate from here, you're kind of a misfit on the question. So the further you are, the worse the fit. Now these fits are actually all pretty good, and these scales are pretty good in developing it. But it turns out that some of the questions that don't fit too well, like number 22 and maybe 21, oh well, no, let's see. These match the heaviest from the Likert scale data, what straight ahead is, and the dry eye question is kind of off a little bit. It's not terrible, but it's off a little bit. And in fact, what the Roche analysis does is it's a good item analysis. So what a lot of people do is they do their Roche analysis. Calculating the Roche score is kind of complicated. So they will use Roche analysis to do an item analysis and find out which questions are good, which ones fit along a single dimension. And then they'll just use the Likert scale, the sum or the mean of the observations, to come up with the final score. And that's what we did with the BIVs. We found, which we eliminated a couple of questions that weren't good, specifically those where the optometry students did worse than the BIVs. So, or the brain injury patients. We don't look at dry eye because dry eye wasn't a symptom relative to other people. It wasn't a good predictor of being brain injury. So we eliminated a couple of questions there and then just took the total to determine people's status in terms of brain injury. Now here is the midterm. And we had a question to determine whether a patient is outside a normal range of patients. We look at to see if his score is outside the mean plus or minus 2 standard errors. Now that turned out to be a pretty difficult question. I think this would be a true statement if this was standard deviations. So a lot of people missed this. I think they just got careless. The word errors is at the end of the sentence, and I think you just looked at it and said, well, most of them are right. Another question was the propensity design. Didn't really get that. Probably didn't cover it in detail enough. The question that was easiest, almost everybody got it. I think everybody got it right. There's a shift in medical decision making from evidence-based to evidence-based medicine. I mean, you didn't have to even read anything to figure evidence-based optometry was going to say true to that question. But basically there was this scale of people getting the questions, and it followed a pretty much a single dimension. There was deviation, but it wasn't bad enough to eliminate any of the questions. All the questions were essentially reasonable. Now, if we look at the frequency distribution, and actually this is from last year. Nobody was really down here in this year's class. You guys did better. Everybody did better. And from last year's test, the people, this is people, and these are items. And you see the items range from pretty hard to easier. And people were kind of clustered up at this end. Now, if we were doing developing a scale like the BIVs, for example, and we wanted to see the seriousness of brain injury, we would want to have people down at this end who are not too brain injured and up at this end where they are, and you'd want the people and the items to kind of match up in terms of distribution, because you want your test to be discriminating between people. Now, this is a midterm, and we hope that people have learned something. And we don't really want people down here randomly distributed across the whole thing, because that means they kind of didn't really learn anything. And so this is kind of a good thing where people are piled up at the end, but there are still questions that are harder than others. That's what a Roche analysis distribution of persons versus items looks like. So what did we look at today? We looked at Likert scales that are used to measure attitudes and feelings, symptoms. They're ordinal data that's treated like interval data by taking means and standard deviations and doing parametric statistics like t-tests and correlations and stuff like that. Roche analysis is used mostly to develop competency scales. And so, for example, like a midterm exam, we look at our Roche analysis to find out if all our questions were basically fair. Do the people that an unfair question would be a question, or a fair question would be questions where hard questions, the people that did well on the test and knew the most, those are the questions they would still get right, and they would get everything right for questions that were easier than that. And a bad question would be one where a person who didn't do very well in the exam got the hardest question right. That shouldn't be, because you should, if you miss a question, you should miss all the questions that are harder than that, and you should get all the questions that are correct, that are easier than that. It never works out quite that exact, but that's the theory. And so if you find a bad, or I always test it, if I find a bad question, I throw it out or revise it for the next time or something like that. There weren't any questions in the midterm that were bad questions, so we looked at all of them. Both types of analyses have the assumption that there is one underlying linear scale. But some scales, like the BIVs, consist of multiple single-dimension subscales, even though they're correlated enough that we counted it as a single one. In some of our analysis, we could also look at separate scales. I know that's a little confusing, but we were right on the edge of a single scale versus multiple ones. So that's measurement, and you will see measurement looked at a lot in the articles that you read, and you hit it every day. Your whole optometric education is going to be on various types of scales that are used to help you diagnose symptoms. That's it. Thank you.